Hi folks, we're going to take a look now at number 2 from the October 4th lesson. So here it's a half-life problem, and it tells us that sodium-14 has a half-life of 15 hours. So that means every 15 hours you lose half of the material that you started with at the beginning of that 15-hour period. Okay, and here they're telling us that we're starting with a sample of 40 grams, and we want to model this with a function. Okay, now there's two ways you can actually do that. Okay, and it all depends on what you use as your input value. Okay, so we'll make A be our amount of sodium 12. Okay, sodium 14. That won't change in either of these models. But in my first option, okay, I'm going to let my X value be the number of 15-hour periods. Okay. Number of 15-hour periods. Okay, so in that case there, if I want to determine my amount, okay, well I have my 40 grams, and I know I have to multiply that by 0.5, okay, to get the amount remaining after my first 15-hour period. And then I take that number multiplied by 0.5 again for my next 15-hour period, and I just keep doing that depending on how many periods I've got. Okay? So here, this models the behavior where X does not represent the number of hours, but the number of 15-hour periods. So if I try to now solve the next problem, okay, so how much will remain after 4 days? Well, I have to figure out now how many 15-hour periods that represents. So 4 days, so 4 times 24, that's 96 hours. Okay, and I divide that by 15, okay, to determine the number of 15-hour periods. Okay, so here we've got 96 divided by 15, and there we've got 6.4. Okay, okay, and so now I can input that into my equation, 40 times 0.5, and it represents our input of 6.4 periods, and from there I can now determine the answer. Okay, so 40 times 0.5 to the exponent of 6.4. Okay, and it looks like we've got about 0.47 grams left. Okay. Now another alternative, okay, which is the one that I would say we'd use more often, is to have a variable that represents number of 15-hour periods is not particularly useful, and certainly it's not a very obvious variable to be working with. So in this case here, I'm going to let X be the number of hours. Okay. This will, however, change my model a little bit. Okay, so I'm still looking for a final amount. I'm still starting with 40 grams. Okay, and I'm still multiplying by half every time. But let's say X represents the number of hours. I'm not multiplying by 0.5 every hour. Okay, I'm multiplying every 15 hours. So what I do is I take my number of hours and I divide that by the half-life period, which in this case here is 15. So you see that we're actually doing the exact same thing as we did before, except we're now incorporating it into the function. Okay, and so now when I input my particular value here and I want to find the amount, I don't have to think about every time figuring out how many periods of 15 hours I need to represent. I can just stick in my 96 hours here, and the divided by 15 is incorporated into the equation. Okay, and again, if I stick that in, I'd get the exact same thing. So while these are both valid models, this is certainly the one that's most common and probably most useful, especially if you have to solve this for several values of X or several time periods. Okay, now let's go to this last thing here that I ask. I say, explain why this problem could not be solved without a calculator. Now, that's a bit of a strong statement, because certainly people would have been solving these types of problems before the advent of calculators. But let's say with the knowledge and the tools that we have, and the problem here is this exponent of 6.4. Okay, And this, now brings into play the idea that exponents move beyond just integer, positive integer values that we're used to working with. Okay, so I want you to think about, how you might deal with an exponent of 6.4. What does that mean? Okay, because when we're defining these exponential functions, they don't necessarily have inputs that are always positive integers. Okay, so we'll leave that for now.